We're ready to start the afternoon sessions, a big one. So the first speaker is Dimitrios Toulikas, who is going to talk to us about the geometry of black hole microstates.
Thank you. Hi all. I would first like to thank the organizers for inviting me to give this talk at this wonderful workshop. So today I'll talk to you about some work I've been doing with several people over the last couple of years, trying to better understand what are the microstates that make up the entropy of black holes. And my talk will be based in these five papers here. So let me start immediately. As you all know, quantum mechanics and general relativity provide extremely good descriptions of our world at respectively small and large scales, and they have been tested experimentally to great accuracy. However, these theories are incompatible, and while both of them describe physics very well in a regime of parameters where the other theory is negligible, the clash between them becomes dramatic when one cannot neglect the effects of either of them. And this happens in particular for black holes, which are thus an ideal playground to forge any theory of quantum gravity. And these theories should be able to address the well-known black hole puzzles. And this talk I will be interested in the entropy one. So, from a general relativity perspective, a black hole is uniquely specified by a finite number of macroscopic quantities, its mass, charge, and angular momentum. But black holes also obey laws similar to the laws of thermodynamics, and in particular, they have a black hole entropy, the famous Beckstein-Hawking one, which is proportional to the area of their horizon. Now, this entropy is enormous, and for example, for the supermassive black hole at the center of the Milky Way, it is of the order 10 to the 90, and according to Boltzmann's entropy formula, this number should correspond to an even larger number of microstates. And you see that there is this huge numerical discrepancy between these two sets of numbers, and the big question is what are these macroscopic degrees of freedom? And this puzzle and the information paradox point towards the realization that we need the theory of quantum gravity to resolve them, and string theory is our best hope for doing that. And one of the most important achievements of string theory is the construction of these macroscopic degrees of freedom as bound states of strings and branes for supersymmetric black holes at vanishing coupling. Here I've depicted the two regimes that are relevant for us. So this D string is the perturbative parameter in string theory, and is the number of branes that we have. And when this number is very small, which this product here controls the coupling between open and closed strings, we can neglect gravity and describe the system in terms of weakly coupled open strings on stacks of D branes. And where this number is large, the D branes backreact on the geometry, and we get a large black hole, which we can describe using supergravity, which is the low energy limit of string theory. Now, all these countings are done in this regime here, but the fate of these microstates when one turns gravity is still subject to debate. But we should know, after all, this is the regime where the information paradox becomes important. And so the question is, take the states that make up the entropy here and try to track them one by one to this regime there. And do they fall behind the horizon and essentially become not visible to a distant observer, or do they manifest themselves through some non-trivial horizon scale physics? And naively, one would first say that as you turn on gravitational attraction, normal objects will become smaller and smaller, and only black hole grows as you increase Newton's constant. So this would mean that this brane system will be eventually engulfed by the horizon and become indistinguishable from the black hole. But luckily for us, there are configurations in string theory that actually expand and never form a horizon. And at its core, the Fuzzball proposal claims that this happens generically and not just for very particular examples. And it claims that there are e to the s non-singular horizonless such systems which resemble a black hole from afar but differ from it in the vicinity of the horizon. And so the black hole is just an ensemble over these Fuzzball degrees of freedom, and horizon singularities appear only because someone is trying to describe gravity using a theory like GR that has too few degrees of freedom to resolve the physics. Now, Fuzzballs are the most general class of objects where the interior of the black hole is supplanted by some new quantum matter that is made of these branes that make the entropy at vanishing coupling. But I will be interested in a subset of these fuzzballs, the ones called microstate geometries, which are the fuzzballs that you can describe in supergravity as smooth and horizontal solutions. And here you can see how such a microstate geometry will look. Asymptotically far away, it's exactly like the black hole, but you see that this infinite thought actually ends up in a smooth cap there. Now, given the difficulty to track these microstates from weak to strong coupling, the quest for understanding what happens to them has been pursued from the opposite direction. Namely, people first construct horizontal solutions that have the same charges with a given black hole, and then count their entropy. And this endeavor has been successful in the sense that a large number of such solutions has been constructed. But for example, for the much studied D1D5P black hole, the largest such family of microstate geometries are the so-called superstrata, and their number is not enough. You see that they give an entropy of this order here, which is parametrically smaller than the entropy of the corresponding black hole. So what we did, we started a new program starting with this paper here that we follow the opposite approach. Namely, we begin from a system that we know that counts the entropy, then we try to track all these microstates as we turn on brane interactions. And in particular, we studied the M2M5P black hole. The brane system is the following. We have M2 branes extending along Y and the M0 direction X11. We have M5 branes extending along Y and 4-dimensional torus. And the entropy in this system comes from the fractionation of each of these M2 branes into N5 strips. So if you take an M2 brane and you put it to be perpendicular to these stacks of M5 branes, this can actually split. And you get all these N to N5 strips that can move independently in the 4 torus directions inside the M5 brane. And if you then go and count in how many ways you can partition the momentum charge into these N to N5 momentum carriers, and also take into account that you have 4 bosonic degrees of freedom because of the 4 oscillation direction, the fermionic superpartners, you reproduce the entropy on the nose. And of course, the question remains, can we track this? And as we go from weak to strong coupling, and the answer is that contrary to the D1D5 system, where the entropy is due to open strings between D1 and D5 branes, which are very difficult to see how they back react. Here we can actually do this, and in order to see how this is done, we have to remind ourselves of this result by Carl and Lasena. So if you have a D1 endicon and D3 brane, the D1 can deform the D3 brane into a spike, so you get basically a D1 spike in the Watt volume of the D3 brane. And a similar thing happens for this setup here. The M2s will pull on the M5s, and the only difference is that now, because of the extra direction of the Y, we will basically have furrows in each intersection, and then you can go on and put momentum waves on them, and in the end, this brane system will look like such momentum carrying furrows in each intersection. This is what we call the super maze, and as a 3-charge system, this preserves for global supercharges. But an important observation is that if you zoom in at any location along this, it locally preserves 16. And in order to get a feel for this local supersymmetry enhancement, the simplest example to consider is just an F1P system. So if you have a fundamental string wrapping Y and some momentum along it, both of them preserve separately supercharges, and together they preserve 8. And you can also form a bound state of this system that still has the same global charges, but locally has 16. And in order to do that, you have to add some transverse dipolar F1s in momentum, let's say along one of the directions of the torus. And so you give a wave profile to the string. And now, if you go and zoom in at any location, you basically see a transversely boosted F1, so it's just a half EPS object. And the general lesson is that you can do this more generally. So if you get a system with some global supersymmetries and some charges, you can make many configurations that have the exact same global properties, but can have an enhanced number of local supersymmetries. And in order to do this, you need to find what is these extra fields that you need to add, that the fields that we call the glue. So for the F1 system, it was just this F1 and P along X1. For other systems, you can have more general things. And this is important because this local enhancement of supersymmetry is the hallmark of the existence of smooth horizontal solutions in supergravity. And I'm saying this because the fact that I will show you that the supermaze exhibits this property will mean that its back reaction should give rise to such solutions. So going to the supermaze, these are the global charges, the original brane system before brane interactions. And it turns out that you need to add these 6 extra fields there. Here I have 3 rows because you can come up with these extra fields, the glue, but just looking at the component 2-charge system. So you take this 2-charge system, and then you see that you need to add these things, and the same thing for the M5P and M2P. So in the end, you end up with this projector that the fact that it satisfies this relation on the Killick spinor means that it's 16 supersymmetries everywhere, and you also have to impose this in order to have the global supercharges. And in general, you take these coefficients to be space dependent, and if you solve the system, you see that it's parameterized by only 2 angles, this alpha and beta. And in M theory, this has a nice geometric picture. It's just this beta angle determines the bending in the X11 and X1 plane that is caused by the M2 branes pulling the M5s. And the angle alpha is the slope of this wave along the y direction. So thinking about the supermaze and also about the similar examples in the microstate geometry program, we will to define this object that we call themelia. Okay, most of you know this here, but themelion is the plural of themelion, which is a Greek word meaning foundation or fundamental structure. And so when you're trying to resolve the microstructure of black holes, you are naturally led to ask what are the most fundamental objects. And of course, the first answer would be strings, but this is not a duality invariant. So you can go on and include all objects that you can get by dualizing strings, like branes or KK monopoles. And you can go even further and include all objects that locally preserve 16 supersymmetries, but when taken as a whole might preserve even less. So these are what we call themelia, and of course things that branes are included, but more generally you can have multiple charges and preserve less supersymmetry when taken as a whole. And we expect themelia to be the fundamental constituents of black hole microstructure, and that's for 2 main reasons. The first is that they are necessarily bound states in the sense that you cannot separate some of the charges without breaking any supersymmetry. And fully backreacted themelion can never give rise to a solution with an event horizon, and the reason for this is that the horizon area in Planck units is a duality invariant number, so you cannot change it by dualities, and you can always dualize locally themelion to, let's say, a stack of KK monopoles, which is just geometry. And as evidence for all of this, in this paper here, we've shown that every known microstate geometries comes from combining themelia, and we conjecture that any such bound states, such coherent bound state of themelia should give us horizonless solutions when we backreact it. And so, as I hope it's clear by now, the supermaze is an example of a themelion that carries the entire black hole entropy. And because it's a themelion, we expect that when we will find the supergravity solutions, that they will be horizonless. And the goal now is to build them, and this is an ambitious goal because of this complicated system of M2 and M5 branes intersecting. And the main, let's say, obstacles are 2. The first is to construct the quarter PPS momentumless background, and then go in that momentum in such a way as to create an 1/8 themelion, a 1/8 PPS themelion. So let me say a few words about the first step. So we want our system to, before brane interactions, to have the charges of M2 branes along time n1, 2, and M5 branes along time 1, 3, 4, 5, 6. And the strategy is to use the 8 Killing spinors of the system to solve the Gravitino equation and then impose the Bianchi identities and, if needed, the equation of motion. So you can do this, and you end up with this ansatz for the metric and the freeform field. Here I've parameterized with t and y and z the M2 directions. This is the plane of the M5 directions, and this is the one of the transverse space. We also include a fibrillation of the M2 direction of the M5 plane, which encodes the bending of the M5 branes by the M2s. These functions A0 and W depend on U, which is the coordinate along M5, as I said, U, Y, and Z. And what you should keep from this slide is that the entire system is completely determined by a single function, this T0, that depends on these three coordinates and satisfies this nonlinear equation. Here, this L, U, and V are the Laplacians in the U and V planes. And if you can find the solution for T0, then using these relations here, you can determine the entire solution, of course, with some appropriate boundary conditions. But this equation is a Donding nonlinear one, and finding a explicit solution is prohibitively complicated. Even a simple solution like an M2 brane, a semi-infinite M2 ending on an M5 cannot be found. So for the moment, I will leave this aside and go and try to address the second problem, that of handling momentum. So, as I said, we need to add momentum, and we need to add it in this way as to create a BPS object, a Themelian object. So this is the precise system that we will use. These are the orange circles represent the global charge that we want to have, the M5, M2, and P. And you see that we need to add these extra 6 fields in order for this object to exhibit this local supersymmetry enhancement. And by going and doing the same process that we did from for the momentum Lie case, and also now we consider the most symmetric subset in the sense that we take the U and V planes to have SO4 symmetry. You end up with this now solution. Here I used light cone coordinates for the T and Y plane, and we take the null wave to be polarized inside this chi direction on the M5 chord volume, and the remaining is a radial coordinate and an S2. And here, this A0 and W are exactly the same as before. So it turns out that the equations for the background completely decouple from the equations for the extra fluxes and momentum. So this A0 and W will still be given by the same Monge-Ampere equation. And then, as for the extra flux and momentum, these are determined in terms of this function P here, which satisfies this modified Laplace equation. Again, this Laplacian this is the Laplacian of the background, so you solve it on the background, and if you determine this P here, you can determine the polarization function K, and then the only thing that needs to be found is this momentum density P, which satisfies this equation. Here I haven't written this because it's too complicated, but you can actually go and replace these three terms here in terms of non-quantities, in terms of W, A0, and this P. So this is also a linear equation. And you can see from this answer that we have all the ingredients that we wanted. So we have the momentum along Y, we have the momentum along chi. For example, these M2 charges are encoded in these terms in the C3 field. And the important point to get from here is that it turns out this second step can be achieved if you assume that you have such a background. And the underlying system is unaffected, and the extra momentum and fluxes that you need to add are governed by a linear system of this background. So this makes us hopeful that this goal of building the supergravity solutions might be a feasible task. And for the remaining time, let me discuss an interesting near brane limit. So as I said, this nonlinear equation is a very difficult one to solve, so we have to somehow simplify our system. And a way to do this is to consider some sort of near brane limit. So we started looking at some solutions found by these people that are whose geometry is of the form of A-3 times S3 times another S3, and everything is grouped over a Riemann surface sigma. And we found that there is a limit, that there's a way to map the asymptotically flat configurations that I have been describing to these ID3 solutions. And the nice thing about the solution is that the BPS equations linearize, so you can find explicit solutions. But the brane interpretation is not clear, For example, we didn't know whether the resolutions really described, let's say, semi-infinite M2 based on M5s, or if we could even find M2s extended between M5 branes. So we started looking at them, and this is the geometry of the setup. So this is the density factor written in Poincare coordinates, the two spheres and the Riemann surface, and all the solutions are determined in terms of a real harmonic function H and a complex function G that satisfy these two equations in a local system of complex coordinates. And as said before, these two, the method that we had before depended non-trivially on three coordinates, the u, v, and z, whereas this depended non-trivially on the two coordinates of the Riemann surface, which I can take to be xi and rho. So we had to find a scaling limit where some of the dependencies due to on the scaling coordinate of the radius and the remaining two of the Riemann surface. And this is the way to map the solutions. These fine tilde functions are not important for discussion. They're just some auxiliary functions depending on the particular setup you're looking. So let's study now a particular example that encodes a lot of the information that the solutions can have. So here I've depicted the Riemann surface, and the solution is determined by these two functions. These two functions have to satisfy some regularity conditions, and in particular, G at the boundary can either be equals to I or minus I. And you can also include some poles in G, and if you include them in the blue region, they will correspond to some M5 branes in the transverse space to the system we want. Whereas if you include them here are the M5 branes we want. That's why I only include some poles there. This is the term that corresponds to the poles. The xi is the location of it, and the zeta is related to the M5 charge being sourced at each pole. And this is the simplest thing you can pick for the H function. It's everywhere 0, and here only it has a pole. And you could also consider solutions that you don't have a flip in G. I mean, you don't have these two places where the function goes from I to minus I. But we wanted to include this because if you take these three solutions and expand near this point near the H pole, where you also have a G flip, they give you ADS4 crosses 7, so this signals the presence of M2 branes there. And in order to really understand what is the brane system that is behind the solutions, you have to move to the asymptotically flat coordinates. And this is the map. The important points are these two. Firstly, because this is the boundary rho equals 0, so this means that this object sits at the origin of the R4 transverse to the M25 system. And if you go at each particular point here and you compute this combination u squared times z, again u is the coordinate along the M5s and z is the normal direction of the M2s, you see that this is constant, and so z is 1 over u squared basically, and from this relation you also get this dependence in terms of the coordinate of the Poincare radius 3. And so the picture is that the M5 brane that is shown there is basically deformed into a spike in the M2 direction, and the radius coordinate sweeps the combined with volume. So that's that's the picture that I just described. This u is the M5 direction, the z is the M2, and to make this even more precise, we can go and compute the M2 charge at each singular point. And if you do this, you get this expression here, and you see that the spike profile, which is basically the M2 sources a harmonic function in the world volume of the M5, and the spike profile is given by this ratio here. So each surface that you have here corresponds to xi, and the steepness is determined by the number of M2s pulling on a number of M5 branes that they're ending on. And since these zetas are all positive, this size increases as you go from a equals to 1 to a equals to whatever value. You get this picture where you have this all these points where, as you go towards the direction you could say it's the xi one, you get more and more steep spikes. This is what we called the Mohawk in this paper. And so it turns out that these solutions describe a single intersection of M2 and M5 branes, but this is far from featureless. So as I said, from far away, it seems that you have a single stack ending on deforming a single stack of M5 branes. But as you zoom in, you see that this background causes them to resolve into physically separated spikes. So you could say that there exists some sort of second level of fractionation. This is the original analogy we used for the supermaze, where everything is fractionated. But if you have some M2s and some M5s, more than one, depending on how many and on how many of the other type of branes, you will get something like that. How much time do I have? Okay, so I will skip this outlook and go to the thing that I thought that we wouldn't have time for. You can even confirm this picture that I said by doing a probe calculation. So this is the initial solution with these 5 poles there, the background, and you can go and add another M5, M2 brane, but now this is a probe, and you expect from the M2 charge that I just showed you that this probe should be able to sit there, and moreover that its location should scale linearly with the M2 charge, and you find that both of these expectations are verified, so you get an M5 brane that extends along a discrete cross tree, and you have to turn on some God volume flux on it to describe the M2 that it has, this spike. And if you go and compute the Hamiltonian in terms of this field pi, which is the conjugate momentum to the flux you're putting there, and compute basically the force along the x direction, you see that it sits at various points, and you get exactly the relation you expect. This is the M2 charge. This is the location of the back reactive sources, but you expect that this will hold also for the probe. So if you take this, divide by the M5 charge, and solve for this psi, you will get basically exactly this relation. So going back, we started, as I said, looking at these solutions because we can actually have explicit setups where we can understand what's going on. And these are singular solutions, so we don't want really to use them for building the supermaze supercrowded solutions, but we expect that there should be some geometric transition where you will end up with just fluxes threading non-trivial cycles. And then the goal is to put momentum on it. And these are the first steps towards the big end goal, which is the supergravity formulation of the supermaze. And if this turns out as we expect it will, this will be finally proof that the microstates of 3-charge supersymmetric black holes are horizonless geometries. So stay tuned for interesting developments, and thank you.
Thank you very much for the nice talk. Questions?
So, do you know the contribution to the entropy of the supergravity solutions? I understand you don't know the solutions themselves yet.
Yes.
But do you know the potential contribution of the supermaze to the entropy?
The idea is because we, as I said, for the supermaze, you can see that in the vanishing coupling limit, it causes entire entropy.
Okay.
Since we know that you can track this and see how each of these brain will turn on, it should give parametrically the entire entropy divided by some number because you need to have supergravity so you don't get everything. But the idea is that we should be able to get this square root of n1 and 5 and p over some number. So yeah, that's we're excited about it because it gives us the entire thing.
Kostas.
I thought the M2, M5, and wave black hole solution is controlled by m small m equals 4 CFT near horizon limit. The solutions that you have immediately controlled by a large m.
So this LDC cross 3 is just the solution that you get in this near horizon, near brain limit in the just in a single intersection. So I wouldn't say that this will be the same for the entire the supermaze.
But still, you really need rectification limit to go from the large m. It's not the small transition from large m equals 4, small m equals 4, but just together I don't think you can get there.
geometry there means that in the more correct case, you wouldn't be able to go away from this.
Yeah, I wouldn't. Yeah, we can discuss that.
Yes, I don't think I agree, but okay, let's. Yeah, okay.
Another question? Carlos?
I missed the comment you made. What did you learn with the probe? And you had a plot there and you say exactly what to expect. I missed that part. Can you
No, the proper calculation is just to check that the interpretation I gave about the solutions of being M2 and M5 spikes is yeah.
You had a plot.
Yeah, no, yeah, I have a plot. Yeah, so
What's that plot?
so this plot is the Hamiltonian of the M5 action. Okay, we're basically reducing we consider D4, but yeah, that's the Hamiltonian of the variant action, and this is the side derivative. This is the derivative along the Riemann surface coordinate, and so you basically determine the force, and you see that this is 0 at these points. So this is where just this M5 M2 spike will sit, and then you see that you get exactly what you would expect from the M2 charge, because this pi, this polynomial is basically the M2 charge of the probe. Yeah, that's a check that the interpretation is correct.
I have one question.
Okay.
At some point you had this 1 ampere nonlinear equation.
Yeah.
Do you know non-trivial solutions to this? Because I think you went to the near horizon geometry, which I assume you developed some extra isometry and probably.
Yes, that's the okay. The only non-trivial solution I think we have for this is a tilted M5 with some M2 on it, so it's not useful.
Okay, this equation pops up in other fields, in ADS-CFT and even in monopole physics. And then there are non-trivial solutions in terms of elliptic integrals. Probably they could be useful in this.
Okay.
I can tell you
Yes,
probably
yes,
later. Okay, thank you very much.
Ναι, νομίζω ότι είχα αργήσει. Όχι, ευχαριστώ.
Our next speaker is Lukas Limanidis, talking about W symmetries, anomalies, and heterotic backgrounds in SU with SU holonomy. Red for that, left, right.
Okay. Thank you for giving me the opportunity to give a talk on this work, which was with George Papadopoulos and Edgar Perez Bolaños. So I decided to have some slides with some theoretical background on this before I jumped to the results. So I will primarily talk about some symmetries of two-dimensional sigma models. So why do we really care about two-dimensional sigma models? Is because they describe the string propagation in a space-time M, where from the sigma model perspective, this is the target space. So given now a connection on this target space where it's not necessarily Levi-Civita, can be a connection with torsion, for example, we can investigate the holonomy of this connection. So what is the holonomy? So given a manifold and a point on a manifold, we can make a loop passing from these points, and we can parallelly transport, for example, a vector. So if along this parallel transport, when it reaches back the same point, the vector has changed, then the transformation that brings it back to the initial state is a holonomy transformation. And of course, the set of all these transformations are making the holonomy group. More generally, if we have a form which is covariantly constant, which means that the nabla hat acting on this form gives us 0, this translates to this relation here, which is the same that we have that follows from the invariance of this form under the group action of the holonomy group. Therefore, if we have a covariantly constant form with respect to this connection, we also know that it is an invariant form of this group. So, given our covariantly constant form, this means that the holonomy group reduces to a subgroup of SO, where in that case this is given by the Berzerk classification. And the reason that these forms are also important in sigma models is because they can generate symmetries. How do they generate symmetries? Given the fact that these are covariantly constants. And this comes as a requirement when we want to set the variation of the action to 0. So since these symmetries arise from the reduction of the holonomy, we commonly refer to them as holonomy symmetries. So I'm also going to call them like this. And the thing is that these satisfy, if we take their commutator, we will see that they satisfy a W algebra. In what sense? In the sense that the structure constants will depend on the conserved currents of the theory, where these conserved currents, of course, can be also currents that they refer to these holonomy symmetries. The interesting thing now is that such forms may arise naturally in the context of the heterotic string backgrounds that preserve some space-time supersymmetry because of the Killing-Spinor, because of the Gravitino-Killing-Spinor equation. And what is the Gravitino-Killing-Spinor equation is coming from the fact that if we have a solution of the field equations and we want this to be supersymmetric, to preserve some supersymmetry, then we have to set the variations of the fermions to 0, where in the heterotic backgrounds we get the Gravitino-Killing-Spinor equation, which is a differential equation for the spinor epsilon, as well as two more equations which are algebraic, and these are the Gaugino and Di Latino Killing-Spinor equations, which include gamma matrices and the fluxes of the theory. If we want to study now the holonomy of this connection, where we take it to be a connection with torsion, then what we can do is to study the commutator of these connections. And since this is a Killing-Spinor and this has to vanish, of course the right-hand side of this has to be 0 as well. Now, if we have such Killing-Spinors, then the holonomy of the connection will be reduced. Again, why? Because then the transformation will act trivially on the spinors, so the holonomy then will be in general a subgroup of the isotropy group of this set of Killing-Spinors. And it is known that the cases that we can have are distinguished between compact holonomies, which are SU2, SU3, and the exceptional case G2, and non-compact, which are given by the semi-direct product of R8 with one of the groups listed here. Now, this is the reason that I said that these forms are naturally arising in the context of the heterotic backgrounds, is because given now these Killing-Spinors and some gamma matrices, we can construct some bilinears that many times we refer to them as Killing spinor form bilinears. So if I mention like covariantly constant or Killing spinor form bilinear, I do mean the same thing actually. And it turns out that these Killing spinor bilinears, these forms, are covariantly constant as a consequence of the gravity Killing spinor equation. Which means now that the isotropic group of the Killing spinor does also leave invariant the forms L. Another thing is that in the context of the heterotic backgrounds, due to the presence of the worldsheet fermions, of the chiral worldsheet fermions, these symmetries may be anomalous. So to preserve the geometric interpretation of these theories, these anomalies somehow have to cancel if we want these symmetries to survive on a quantum mechanical level. So in this work, I consider SU2 and SU3 holonomies, and at the same time, these Killing spinor bilinears are already known. So the goal is to find the algebra of these symmetries and verify that these indeed make a W algebra. Another goal is to find the anomalies, find an expression for the anomalies of these symmetries, and then argue about possible ways to cancel them. So the setup is, as I said from the beginning, a two-dimensional sigma model, which has 1,0 supersymmetry. And the classical fields are the target space coordinates and the chiral fermions. We also have the metric, the B field, and omega is the connection of the vector bundle over the space-time. So what are the symmetries of this action? Just a general overview. So we have diffeomorphisms of the target space. We have gauge transformations parameterized by U of the gauge sector with the connection capital omega, which I distinguish with this lowercase omega, which is the frame connection, as we also have space-time frame rotations parameterized by L. We also have gauge symmetry of the B field, which can be, a variation of it can be an exact form. And we also have the holonomy symmetries, which are the ones that I wanted to talk mostly about. So the transformations now on X and psi are given from these relations. And this will be symmetry of the sigma model action, provided that the forms are covariantly constant, and also they satisfy this equation as well, and that the parameters of these transformations do not depend on the double minus direction on the superspace. The first one, we can recognize it as a consequence of the Killing spinor equation, which I already mentioned before. And the second one is a consequence of the gauge-Gino Killing spinor equation, which was one of the other algebraic Killing spinor equations that we have, but I didn't mention before. And since we want to identify conserved currents in the structure constants of these of the commutators of holonomy symmetries, we also provide the expression of such currents. Now, if this seems a bit abstract, just keep in mind that if we set L equal to 0, then we have a Killing vector. Okay, so when we wanted to find the commutator of such holonomy transformations, we also wanted to write, since this is also a symmetry of the action, we also wanted to write it explicitly as a sum of individual transformations which are symmetries of the actions too. So for this reason, we also needed to include one more transformation which ends up being a symmetry of the action, this S. generated by S. This S is not a holonomy. This delta S is not a holonomy transformation. And this Q, although it is taken to be covariantly constant, it is not constructed necessarily from Killing spinor. So it's not a Killing spinor bilinear. And this also includes the special case of the transformation of the stress energy tensor. Now, what can we tell then about the anomalies of these symmetries on a quantum level? So if, let's say, delta A, if the generator A, if this symmetry is anomalous, then the variation of the effective action, denoted here as gamma, will give us the expression for the anomaly. And plugging this into the expression for the commutator, we can see that it has to that both anomalies, potentially both anomalies generated by A and B, have to satisfy the so-called Wess-Zumino consistency condition. And this is what we're going to use in order to find an explicit expression for the holonomy anomalies. But to do so, it will be convenient to have already an expression for the anomalies of the frame rotations and gauge transformations, which we can combine by using the Wess-Zumino consistency condition and find the desired expression. So then the anomalies of the associated with the frame rotation is determined by the descent equations, and the same happens, of course, for the anomaly of the gauge transformations. And to see that, you need to start from the trace of the R wedge R, which R is the curvature of omega. And since this is closed, by using the Poincaré's lemma, we can write it locally as an exact form, where now this Q03 is the Chern-Simons form. But at the same time, this is invariant. So it's a zero missing here. So this is invariant under this transformation. And therefore, the variation of the Chern-Simons form can be written again as an exact form, this Q12, which we use now to express explicitly the anomaly of the frame rotations. And in exactly the same way, somebody can find the anomaly of the gauge transformations by having in mind that now these transformations will commute. So then the right-hand side has to be 0. So this anomaly will come now with a minus sign here, and of course, replacing here the appropriate connection and parameter. And we don't need to worry about these anomalies, because it is already known how to cancel this. And this can be done by assigning an anomalous variation to the B field. So coming now to the point to describe the anomalies of the holonomy symmetries, we use again the fact that holonomy symmetry commutes with a frame rotation or with a gauge transformation. So we can plug in now the expression that we have it has to be twice. One time we have to do it for this anomaly, and the other time for the gauge anomaly. So we plug this into this equation. The right-hand side has to be 0. And then we try to solve for the anomaly of the holonomy symmetry. And we find that this will be written in terms of the Chern-Simons form, where now this is just the difference of each Chern-Simons form of the frame rotations and the gauge transformations. Now, when it comes to the cancellation of this, we may adopt two different scenarios. The first one is to consider that the bilinears do not receive quantum corrections, and the second one, that they do receive quantum corrections. So in the first case, what we can do is that we can exploit the fact that the Chern-Simons form can be specified up to an exact form dw, where w is just a two-form on the space-time. And when it comes to the second scenario, what we need to observe is that if we try to express explicitly now the expression of the anomaly, what we find is these three terms, which maybe seem messy, but you can just focus on the blue part of it. So what does this tell? That if these vanish independently, then the anomaly will cancel. And we expect that this might happen because the first term is proportional to the nabla hat of L, but both the form and the connection are corrected. The second term is the second condition that we have for the action to for the variation of the action to vanish. So let me go a bit back to remind you. So these were the two conditions that we have again, but now where both the connection and the bilinears and the fluxes are corrected. And given, of course, that the connection now will be written in terms of the corrected flux, which include this Chern-Simons term. So now, if this vanish, then we expect the anomaly to cancel. And actually, this is also consistent with the fact that the Killing-Spinor equations of heterotic supergravity, up to and including two loops, we know that they retain their form given that we have replaced H with the corrected H. Therefore, by solving the Killing-Spinor equation with respect to the corrected connection, we expect to find some corrections on the spinors, and therefore the bilinears will also incorporate these connections. So given that this is this holds, then we expect the anomaly to cancel. Now, before I present the results for the SU2 and the SU3 holonomy backgrounds when it comes to the algebra of these symmetries, I give you the general result of what we expect to find, so the first term is again a holonomy symmetry, and the parameter of this depends on the individual parameters of the delta L and delta M. The second term, of course, is against the symmetry, and it is the transformation that I introduced before, and this is not the holonomy symmetry. And the third term, although it includes holonomy symmetries, it differs on the level of the parameter of the transformation, because now this parameter includes conserved currents of the theory. So in particular, when we're talking about backgrounds which admit a connection with SU2 holonomy, then the holonomy symmetries we have are one forms and two forms. The one forms are the isometries of the space-time, and these two forms are in fact three complex structures because the base space. So we consider this space-time as a principal bundle with a base space, with a four-dimensional base space, which is a hyperkähler manifold with torsion, and a hyperkähler manifold with torsion incorporates three complex structures. And then now the variation of the symmetries will be given by these expressions. We also need to include one more symmetry in the right-hand side, where this is related to the quadratic Casimir operator of the Lie algebra of the isometries. And schematically, the commutators will have this form. The first one is no surprise. It's just the Lie algebra of the isometries, so it closes in the isometries as well. And the last one, although I avoid to write too many details, I would like to focus only on the third term, where the coefficient includes the currents of the isometries, which is defined in that way. And this is the reason that we say that we have now a W algebra generated by the holonomy symmetries of this background. Now, a comment is the following, that if I also include this transformation, where now HAB is covariantly constant, and the ABC refer, by the way, to the fiber indices, the fiber direction, sorry. Then this J, these currents, are being absorbed by this transformation, and therefore they are not, they wouldn't appear as a part of the parameter. And therefore, in that case, we wouldn't have any such dependence and not a W algebra. So by defining and by introducing new transformations, we can write this also as a Lie algebra. But we prefer to keep it within the context of W algebra as a more economical approach, since we have to introduce less transformation anyway. It's well, I mean, it's W algebra in the sense that the coefficient, the parameters depends on the currents. That's all. Yeah, not only that.
Not linear on the right hand side.
No, because they can also depend here quadratically. And sometimes they can be even higher powers. Yes.
W algebra is the first one W is the object. So what is
I do not know this.
Is Virasoro part of it?
Well, we do say that the W algebras are extensions of the Virasoro algebras.
Yeah, but then the question Kostas asks is invalid. Anyway, maybe later.
I do not think so.
more like Sugawara structure?
Sorry?
Is it more like a new energy momentum tension? Quadratic with current.
It's quadratic in currents, and yeah, and
It's more like has dimension 2.
this has dimension 2 because we don't find, if we write it like this, yes, because otherwise then it would look like the Lie algebra if we introduce the other generator. Yeah. And given also the transformation of the quadratic, which are related to the quadratic asymmetry, we can also write down the commutators with the other holonomy transformations, which depend again on the currents, but not necessarily quadratically. Can be even in that case just linearly. That depends on each case. So when it comes to the cancellation, maybe I don't have time to discuss much about it, but the idea is to use the W that I introduced before. We said that this Chern-Simons form can be written up to an exact form DW to define and therefore define the counter term in that way. So if we do so, then the pullback of the Chern-Simons of the base space has directions. The indices of it are only the base space. So then a transformation which which is along the fiber directions contracted with this will make this term to vanish, and therefore the anomaly to vanish. So this happens for the isometries and the associated Casimir operator, but it doesn't happen for the complex structure, which is on the base space, and we need to insert another counter term to make this vanish. When it comes to the SU3, the landscape is very similar because, again, we have one forms and two forms, which are, again, isometries and the complex structure. But the new thing we have here is that we also have three forms. So the algebra now of these three forms, the algebra, by the way, of the other forms is identical, so that's why I do not write it again. So now the algebra of the three forms with the other holonomy symmetries will have this form, where now almost all the parameters, apart from one, it depends on the currents of this transformation. And in that case, if I remember, you can have also cubic in the currents. And again, we are able to cancel the anomalies by adding finite local counterterms to the effective action for the isometries, the Casimir, and the complex structure, like in the SU2 case. But if we also consider the case where the bilinears do receive quantum corrections, then we can again cancel all the anomalies in the way that I described before. So to sum up, what we did was that we found the algebra of holonomy symmetries for backgrounds with connection with SU2 or SU3 holonomy. We found an explicit expression for the anomaly of each case, and we also argued that we can cancel some of these anomalies either by using finite local counterterms to the effective action or by assuming appropriate quantum corrections to the bilinears. Another case which is left is in order to conclude the compact holonomies, is the G2 case, which has again one forms for the isometries, and it also has three forms and four forms. So maybe we expect some more complicated expressions for the commutators and the algebra. That's all. Thank you very much.
Questions?
So I have two questions, so they're related. So the first one is like the coefficient of these anomalies, right, of this holonomy symmetry. So it's related to the
You have to do
Lorentz and the U1 anomaly.
you have to do the explicit computation, which is
No, but I mean, from the expression that you have in the end, right? I mean, it must be related to the anomaly coefficients of the Lorentz and
this, yes, this coefficient, yeah.
yeah. So
Yeah.
it's not an independent
No.
anomaly coefficient.
No, it's not independent. It also comes from this coefficient here.
Yeah. Okay. So it's not independent anomaly coefficient. Okay. And the other question is like, have you tried gauging this
No.
holonomy symmetry?
No. But I think that there is something in the literature in simpler cases.
Okay.
Yeah, I think there is something in the literature by Hall.
One offset supergravity, right? To do that.
Yeah, you could gauge them, I guess. Yeah, but these are semi-local. They do not depend only on the double minus direction, but they do depend on the double plus and the plus, of course, direction. Yeah, but no, we have not tried to gauge them.
It seems that in all cases it's a trivial, right? You cancel them in all cases.
No, there is one left, which is for the three form, and within the context of the SU3 holonomy. So for this, we are not able to find any local counter term to cancel this. But within the context that we consider quantum corrections, yes, in that case, all of them cancelled by default is what I showed in the.
Yeah, you said you deform the quadratic term with the transformation. You have quantum correction, and then you cancel it.
Excuse me, I didn't hear.
I thought you said you either cancel it with a local counter term or by deforming the transformations by quantum correction.
Yes, exactly. By deforming both the bilinears and the connection such that the corrected bilinear is covariantly constant with respect to this corrected connection.
So from this perspective, all anomalies is trivial.
Yes. But this also, I mean, these two ways have an assumption in the beginning, which is if you want to have if you want to add the finite local counter terms in the action, then the forms should not be corrected. And in the other case, of course, they are corrected. So depends. It's not. I feel it's not written on the stone after all.
There's no abstraction engaged with. No cases engaged.
No, I didn't say anything about gauging. I just said like depends on what you have, because maybe, for example, you have a complex structure which is constant and you don't expect it to get quantum corrected. So in that case, you would use a local counter term to cancel the corresponding anomaly of this second supersymmetry.
My question, I have one. What is the dimensionality of this W algebra that you have?
We didn't work further on that. Like it was just we just found that it depends on the conserved current at the right-hand side, and we just.
Is it closed?
It's closed in the sense of the type of the transformation that you see in the right-hand side. You don't expect to find anything else for both SU2 or SU3 cases, and maybe for G2.
One of the known ones. That's why I'm asking. This is the classical level.
Yeah, maybe that would be for future work.
Okay. Thank you very much.
You're welcome.
Okay, the next speaker is Nikolaos Liatsos on the lack of scale-separated supersymmetric ADS2 flux vacua.
So, first of all, I would like to thank the organizers of this workshop for inviting me to give a talk. So my talk will be based on a recent paper that I wrote in collaboration with Niccolò Cribriori and Fotis Farakos, in which we argued that supersymmetric antidesert vacua in 2 dimensions that are supported by fluxes cannot be scale separated. So in this talk I will present our main general argument, which I will illustrate with a specific 2-dimensional supergravity model, as well as with examples from flux compactifications. So to begin with, a given vacuum that arises from a compactification is characterized as scale separated if the dimensions of the internal compact space are much smaller than those of the external space-time, so that a lower dimensional effective description indeed makes sense. Now, from a top-down perspective, an antide vacuum is scale separated if its radius is much greater than the Kaluza-Klein length scale, while from a bottom-up perspective, scale separation is actually this hierarchy between the ADS radius and the ultraviolet cutoff of the effective theory. Now, a vacuum that satisfies one of 1 and 2 is scale separated and can explain why only an antide Sitter factor of spacetime is large enough to be visible at low energy. Now, an advantage of the bottom-up approach to scale separation is that the ultraviolet cutoff does not necessarily need to have a geometric interpretation, while the Kaluza-Klein scale is typically related to the geometry of the extra dimensions. Now, this approach has been used to prove that maximally supersymmetric antide Sitter vacua of n equal to 2 and n equal to 8 supergravities in 4 and 5 dimensions with a residual abelian gauge symmetry cannot be scale separated because the absolute value of the scalar potential at such vacua is of the same order of magnitude or greater than the square of the ultraviolet cutoff that is postulated by the magnetic weak gravity conjecture. Now, the most well-known setup that gives rise to n equal to 1 supersymmetric ADS4 vacua that are scale separated is the DGKT1, where in such a setup the construction of scale-separated ADS for vacua is achieved by compactification of massive type 2A supergravity on a Calabi-Yau threefold in the presence of flux in O6 planes. Furthermore, scale-separated anti-Dester vacuum in 3 dimensions have been constructed by flux compactifications of type 2A supergravity on 7-dimensional spaces with G2 holonomy. However, to date, no scale-separated anti-Dester vacuum in 2 dimensions has been constructed, and we have provided a bottom-up explanation of why supersymmetric under-sitter vacuum in 2 dimensions that are supported by fluxes cannot be scale-separated. So, for an ADS2 vacuum, the cosmological constant lambda is related to its radius L by this equation, in which the 2-dimensional Planck scale does not appear. Now, an ADS2 flux vacuum is supported by an electric field strength with components along the ADS2 directions, according to this equation. Now, in principle, we can have 2 such different ADS2 vacua that are supported by fluxes of this form, which are separated by a domain wall particle. Now, in these equations, alpha and beta are 2 real constant, and epsilon 2 is the Levi-Civita tensor associated with ADS2. Now, the tension of such a particle sets an upper bound on the ultraviolet cutoff of the 2-dimensional effective theory, and if the domain wall is also a BPS1, which means that its tension is equal to the absolute value of its charge, we obtain this inequality between the ultraviolet cutoff and the charge of the domain wall particle, which is reminiscent of the magnetic weak gravity conjecture. Now, the change in the F2 flux that is induced by the domain wall is dictated by its charge Q, and if we impose flux quantization, where n is an integer number, then the inverse of the radius of one of the 2 ADS2 domains is at least of the same order of magnitude as the ultraviolet cutoff. So the natural interpretation of this relation is that supersymmetric ADS2 flux vacua are not scale separated. Now, there could also be a contribution to the cosmological constant that is not related to any two-form flux, which we have denoted by plus or minus lambda squared. Now, the positive sign is beyond the scope of our work, since a positive contribution to the cosmological constant means that there is at least one sector that spontaneously breaks supersymmetry, and we studied supersymmetric ADS2 vacua. On the other hand, an additional negative contribution to the cosmological constant that is not induced by any flux can only make things worse as far as scale separation is concerned, because this contribution to the vacuum energy is already at least of the same order of magnitude as the ultraviolet cutoff squared. So the presence of a flux-induced term in the vacuum energy is enough to exclude scale separation for supersymmetric under-Ste vacua in 2 dimensions. Now, let us now consider the n equal 1,1 supersymmetric extension of Zakiv-Teitelbaum gravity. Now, the field content of this model consists of the supergravity multiplet coupled to a dilaton multiplet. Now, the supergravity multiplet in 2 dimensions contains the Wilbur Majorana gravitino psi mu and a real auxiliary scalar A, while the dilaton multiplet contains a real scalar phi, Majorana fermion lambda, and an auxiliary real scalar F. Now, the offset action that describes this system is given by equation 15, where L is a real constant that has dimensions of length. Now, varying this action with respect to the component fields of the dilaton multiplet, we obtain these 3 equations. In particular, equation 18 indicates the presence of an ADS2 vacuum with radius equal to L. Now, to give the two-dimensional cosmological constant a dynamical role, we replace the auxiliary field F of the dilaton multiplet by 2-form H2, which is locally the field strength of 1-form B1, according to equation 20. And actually, taking the local supersymmetry variation of this equation leads to an integrable equation that provides the local supersymmetry transformation rule for the one form. So after this replacement, the action for the system takes this form. So this is essentially the action for an one-form dilaton multiplet coupled to the two-dimensional n equal to 1,1 supergravity. So after integrating out the auxiliary field A, the equations of motion for the one-form B1 are given by 22 up to terms with fermionic fields. Therefore, the Hodge dual of H2 divided by phi is a constant. Then, varying the action with respect to phi, we find this expression for the two-dimensional curvature, and for non-zero C, this equation describes an ADS2 space-time with length scale L that is related to the constant value of this quantity by this equation. Now, we now consider a particle in two dimensions that is coupled to the one form B1. Now, such a particle is described by an action of this form, where W1 denotes the word line of the particle, which is parameterized by a single coordinate tau. Capital X mu of tau are the values of the space-time coordinates on W1. Q is the real charge of the particle under the one form B1. And a dot indicates a derivative with respect to tau. And we consider the action that is the sum of this bulk action and the particle action. Now the equations of motion for the two-dimensional dilaton phi, the one form, B1 and the metric, are given by 28, 29 and 30 respectively. And now let T and X be the coordinates of the two-dimensional target space-time. Now, if the particle lies on the axis x equal to 0, then in the static case, the x component of the equation of motion for the one form takes this form, and if we integrate this equation over an interval of this form where epsilon is a positive real number, we find that the difference between the constant values of the Hodge dual of H2 divided by phi for positive and negative x is given by this equation, so it is clearly determined by the charge of the particle Q. Now, if neither of A plus and A minus is 0, then both of the regions x positive and x negative are two-dimensional Arndt de Sitter spaces with radii L plus and L minus, given by this equation. So the inverse of at least one of these two radii is of the same order of magnitude or greater than the ultraviolet cutoff, which clearly implies the absence of scale separation. We have also solved the equations of motion that govern the dynamics of the system for a charged domain wall particle that lies on the axis x equal to 0 in the static case. We started from these ansatz for the metric, the dilaton, and the one form, which are compatible with time translation symmetry. So if the charge Q of the particle and the dilaton have the same sign, then the functions phi, f, and b that solve the equations of motion are given by these three equations, where alpha is a real constant and h is the Heaviside step function, while if the charge 2 of the particle and the dilaton have opposite signs, then the equations of motion are solved by these three functions. And we also determined the killing spinors that are associated with the previous bosonic background. Now, in both of these cases, the particle solution preserves half of the n equal to 1,1 supersymmetry of the background space-time, as can be deduced from the conditions 44 and 46. So the particle solution that we derived is indeed a BPS1. We have also examined solutions of type 2 supergravity of this form that feature an electric Ramon-Ramon flux F2 with components along the external edges to space-time, a magnetic Ramon-Ramon flux F4 that wraps 4 cycles of the form S2 times T2. Also, we have 0 Romance mass and vanishing Neves-Schwarz 3-form flux H3. We also have a constant n-dimensional dilaton. And furthermore, there are not any localized sources. And now such solutions arise as near horizon limits of configurations of intersecting D0 and D4 branes. And in the near horizon limit, the branes dissolve into fluxes. Now these are the equations of motion in the Einstein frame for constant dilaton. 48 is the trace reversed Einstein equation. Equation 49 follows from the variation of the 10-dimensional action with respect to the dilaton. And 50 are the Bianchi identities in equations of motion for the Ramon-Ramon field strengths. Also capital letters of the Latin alphabet label the coordinates of the 10-dimensional space-time. And we have also introduced this notation. Now, from the Einstein equations and the equations of motion for the dilaton, it follows that the Ricci scalar of the two-dimensional external space-time is given by this equation, where F8 is proportional to the Hodge dual of F2. It is a magnetic flux. And now from this flux quantization condition, it follows that the squared modulus of F8 has this form. Therefore, the two-dimensional curvature is given by this equation, from which we can read off the radius L of ADS2. And for simplicity, we have taken the square of the 10-dimensional gravitational coupling constant to be equal to 1/2, which gives this value for the string length. Now, this scale is actually related to the tension of a D0 brane that is smeared along the 8 compact directions. We can actually deduce this tension by actually determining the back reaction of such a D0 brane on the two-dimensional curvature. So we start from the action for a D0 brane in 10 dimensions in the Einstein frame, where T0 is a real constant that is equal to the inverse of the string length, and mu0 is the real charge of the brane under the Ramon-Ramon 1 form C1. Now, the D0 brane contributes these terms to the 10-dimensional Einstein equations, where T0 Mn is the energy momentum tensor associated with the D0 brane, and T0 is its trace. So, if the word line of the D0 brane is described by these equations, then in the static case, we find that the trace of the associated energy momentum tensor is given by this equation. So the contribution of the D0 brane to the curvature of the two-dimensional external space-time is actually proportional to TD0. We then smear the D0 brane along the compact 8-dimensional internal space by actually performing this replacement, where G8 is the determinant of the metric of the 8-dimensional internal space. So in this the back reaction of the smeared D0 brane on the two-dimensional curvature is given by this equation, from which we can read off the tension of the smeared D0 brane from a two-dimensional point of view. And we can see that the tension of the smeared D0 brane is of the same order of magnitude or less than the inverse of the ADS2 radius, which is in accordance with our general argument against scale separation. Now, let us also consider a more general type 2 setup with an ADS2 solution that is supported by a magnetic flux Fn, according to this equation, where the precise numerical coefficient depends on the way in which the various fluxes are related by the equations of motion. Now, from this flux quantization condition, where sigma n is the n cycle that is threaded by the flux Fn, we find that the two-dimensional curvature and the inverse of the ADS2 radius are given by equation 69 up to numerical coefficients that are of the order of 1. Now, we assume that the Hodge dual of the magnetic flux Fn, which is an electric flux, is sourced by a dB brane with where P is equal to 8 minus n, that is electrically coupled to the Ramon potential C9 minus n. We then split the coordinates of the 8-dimensional internal space as x high equal x I hat, comma x I tilde, where x I hat are the coordinates that are tangential to the n cycle sigma n, and are also parallel to the world volume of the dB brane, while x I tilde are the internal coordinates that are normal to the n cycle, but are transverse to the dB brane. We also assume that the metric of the internal space splits according to this equation. And if the D8 minus n brane lies on this hypersurface, its back reaction on the two-dimensional external curvature is given by this equation, where this constant coefficient vanishes for n equal to 5, that is for D3 branes in type 2b, and it is of the order of 1 for all other possible values of n. So we again smear the D8 minus n brane along the n cycle sigma n by performing this replacement. So in the smeared approximation, the back reaction of the D8 minus n brane on the two-dimensional curvature is dictated by this equation. So as far as its back reaction on the two-dimensional curvature is concerned, this dB brane actually behaves as an effective D0 brane with a tension given by equation 74, again up to a numerical coefficient that is of the order of 1. So this tension is again of the same order of magnitude or less than the inverse of the ADS2 radius. So such flux supported ADS2 vacua in type 2 compactifications are not scale separated either. So to conclude, we have provided the bottom-up argument that excludes the existence of supersymmetric scale-separated understay vacuum in 2 dimensions that are supported by fluxes. Our argument relies on the existence of a fundamental BPS domain wall between 2 such vacua, and the tension of such a domain wall is an upper bound on the ultraviolet cutoff of the 2-dimensional effective theory. Now, if scale separation is possible at all in 2 dimensions, it is most likely to occur in setups with at most 1 supercharge. Such a model could, for example, be constructed by compactifying type 2 superstring theory on a manifold with spin 7 holonomy, which preserves 1/16 of the original supersymmetry, and then performing an appropriate oriented fold projection to further reduce the amount of supersymmetry by a factor of 1/2. But we have left such an investigation for future work. So thank you very much for your attention.
Questions?
So it was unclear to me where you use supersymmetry in this. It's clear the approach you take with the Einstein's equation. Where it comes the need of 1 supercharge for this not to be valid?
Yeah, because we have one of our assumptions is that the background space-time has enough supersymmetry in order to be able to support BPS objects. Because in our general argument, we require that.
This part I understand. The second part, you only seem to use the Einstein's equation.
Yes.
This part I understand, but
Okay.
when you move to the next part, in the generic case, you only seem to use the Einstein's equation. Where here, from
Yes.
here on, you don't seem to be using supersymmetry. Why the need of 1 supercharge per cell?
Well, actually, this D0 brane is also a BPS1 because this mu0 is equal to T0, I think. So, yeah, I haven't said that explicitly, but yeah, we need.
You need the T0 to be BPS.
Yes, exactly. Of course.
What would go wrong if you had scale separated? What has to go wrong? What has to be different
To
had scale separated? Right? What needs to be different?
well, we have not actually examined this issue. What we wanted actually to show that we wanted to provide a general argument against the existence of 2-dimensional antidecider vacua that are supersymmetric, supported by flux and scale separated.
I think he's asking there is some inequality that we showed at the beginning. Which one is violated if there is scale separation?
Yeah.
It's simpler.
Okay. We actually we actually violate this inequality. We compare the radius of the ADS2 with the ultraviolet cutoff of the theory, and of course the ultraviolet cutoff of the theory is bounded from above by the tension of a BPS domain wall.
example is known in the 90s. I don't know. It looks like he presented it as a new, but all of this is known from the 90s. The example is that he had the smear, the zeros.
Yeah, we actually
90s, the 10 years before that. By 1990s, mid-1990s.
yeah,
The
we
Use
actu-
to process 2 is not 70
yes.
Robinson Berkovitz. Then within supergravity is known from the 80s and mid-90s. Within dissections is known from 95 to 2000. I don't think there's any new solution. It comes from the symmetric bearing intersections with
Okay.
this near brane. And I think the one with the d zeros is, I know the intuition.
Actually, it is not known that you cannot have scale separation in ADS2. It is not known. Actually, people are searching for
For
this
the
solution
ADS2
for years.
and for the supersymmetric case with the d0 brane,
No, forget the D0. Take some flux background and try to find ADS2 times something. There is no known solution that is scale separated. And people are trying to find it for years.
yeah, but I'm saying the scale, the ones where you do not have scale separation.
Oh yeah, without scale, without scale
All
separation, there
non-supersymmetric
are a lot, of
solutions do not
course.
have,
Yes.
yes. All
Without scale
usual,
separation, there are a
yes,
lot, of course.
yes. All standard
Anything that is
cases.
holographic is without scale
Yes,
separation,
yes,
of course.
yes, yes.
But we wanted to show the opposite. That the thing that people are trying to find for years cannot be done if you have more than one supercharge.
Yeah, it's the example at the end that I'm saying is not.
Yeah, that example is just a toy model so that you can write it down and get a handle on how things are working. But then he showed also the generic case and showed that if you forget the S2, again you have the same problem actually. It's never really good with S2.
Okay, let's thank the speaker again. Ευχαριστώ πολύ. Εικόνα για να δείχνεις πίσω τους οδούς. Θα σου δώσω 10 λεπτά. Σε πω ευστάθειο. Εκεί δεν το περίμενα. Πώς θα το πούνε. Στάθη. Okay. The next speaker is Stathis Vituladitis, talking about gifts from infinite dimensional current algebras.
Right. First, let me thank the organizers for putting together this wonderful workshop and for giving me the opportunity to talk here. And yeah, it's a Christmas workshop, so I came bearing gifts. And the title will be evident in the first few slides. It's based on basically these two papers that came out this year and the last year with Diego Hoffman and Jackson Fliss, respectively, and some ongoing thoughts or work or whatever. All right, so the plan of the talk is mainly that I'll motivate what I'm studying and why, and then I'll start playing with free fields, basically, to set the stage, and then the gifts will come. There will be one gift in gapless theories, in conformal theories, and one gift in gapped systems, mainly in topological order. And then I'll have some gift ideas for next year, perhaps. All right, so the idea is that symmetries are a very powerful thing in physics, in quantum many-body systems, in quantum field theory, and this is manifest in terms of imposing infrared constraints in the form of a Landau paradigm or its weaponization, Landau-Ginzburg theories, as well as a 't Hooft anomaly matching, as well as in quantum field theory selection rules about amplitudes, decays, transitions, and so on. And in quantum many-body systems, in terms of phases of matter that are protected by something, by symmetry, topological insulators, topological superconductors, as well as the more exciting fractons, fraction phases, and so on. And then it goes without saying that since symmetry is so powerful, having infinite dimensional symmetry is ultra powerful. And it suffices to look at two-dimensional CFTs, where the conformal algebra itself enhances to an infinite dimensional version thereof, called Virasoro algebra, that fixes exactly the spectrum, and it underlies string theory and has connections with quantum gravity and so on and so forth. And moreover, also internal symmetries enhance in the form of a Kac-Moody algebra, which is also infinite dimensional and is connected to, so for example, rational CFTs that have Kac-Moody algebras are much more constrained in their connections with three-dimensional topological QFT. And as a physical example, one can use these Kac-Moody algebras. This example will come back in the future, in the next few slides, to pin down the entanglement spectrum of fractional quantum Hall states. So there's one downside that seems obvious here, is that only in 2 dimensions can I have those things? Well, the purpose of this talk is to say that not really. I will not have a Virasoro in higher dimensions, but I will have a Kac-Moody. So in order to do that, I'll need to employ a recent generalization of the concept of symmetries. And there are many papers, so I couldn't cite all of them, so there's a mandatory if you know, you know citation. But one kind of those generalizations that I'll be using goes by the name of higher form symmetries, as formalized by these people there last 10 years ago. And the idea is the following, that a regular symmetry that you're all used to in its continuous version has a conserved current, which in adult language, in adult-friendly language, is a co-closed one form. And exponentiating that thing, well, first of all, integrating that thing on a codimension 1 manifold gives you a conserved charge, and exponentiating that thing is an operator that acts on the Hilbert space, that is topological. And now the generalization to higher form symmetries is very simple. I just replace the conserved 1 form to a conserved p+1 form, which means that then to get a conserved charge, I have to integrate it on a codimension p+1 slice. And these things act by linking. So if I have an extended operator, so these things act on extended operators, in contrast to zero form symmetries or regular symmetries, which act on local operators. Higher form symmetries act on extended operators by linking with them. And there are also other generalizations that I will not use in this talk, but feel free to ask me later. So now let's get to the meat of the talk. And the star of the show will be a free p-form field. What do I mean by that? I mean something that whose equations of motion, whose dynamics are governed by these two equations. Or in adult-friendly language again, there's a co-closed p+1 form that is also closed. So a harmonic, essentially, form. And I'll be denoting the Hodge dual of the p+1 form as J tilde. Now, of course, you may object that this is a very simple example. Nonetheless, I'll use it to learn something new from it. And in fact, if I write the EFT for this thing, it's just generalized Maxwell theory, and I'll constantly be in this sort of Maxwell theory setup. Now, this indeed describes essentially p-form photons or their magnetic cousins, magnetic photons that are d minus p minus 2 form. And it has a lot of symmetry, which I can and use to and will use to utilize to solve this theory on any topology. So let me start with what symmetries it has, and the sort of almost textbook by now symmetries that this theory has is a p-form U1 symmetry dubbed electric, and a d minus p minus 2 form symmetry dubbed magnetic, again U1. And its generators, the generators of this symmetry are just these conserved charges that I talked about before. A codimension p+1 operator and a codimension d minus p minus 1 operator that act respectively on Wilson lines and at 't Hooft lines. Essentially, there's an electric story and its magnetic dual. Say, if you get lost with indices, just replace p equals 0 everywhere, and you're in a compact scalar setup where you know what these are. These are just the vertex operators, and these are disorder operators. Very good. So now I talked about this textbook almost symmetries, but there's much more to it. In fact, there are infinitely many more zero-form symmetries, so normal symmetries that you all know and love. And you can convince yourselves that, first of all, this thing is a one-form, that you can just add indices. And secondly, that this thing is conserved. If and only if these parameters that I've introduced here, so I've introduced two parameters, two functions, one p form and one d minus p minus 2 form, lambda and lambda tilde, such that this whole thing is conserved if and only if these guys satisfy a sort of a twisted self-duality condition, meaning that the derivative of one is the Hodge dual of the derivative of the other. Much like, say, for example, photons and their magnetic duals. And indeed, this yields conserved charges, which only depend on the manifold they're defined on topologically. And it acts both on local and non-local operators, and wait for gift 1 to see how. And more importantly, I can compute commutators between these two things. And in contrast to higher form symmetry, so it's one thing I did not mention before, is that higher form symmetries are abelian. There's enough space in space-time that I can pull the charges out and change the order that they act on my fields. However, these things are not necessarily abelian, but they descend from abelian theory, so the commutators is only central. There's nothing there. Nonetheless, there's a non-trivial commutator that will generate the spectrum in a bit. And as an example, let's go back to d equals 2 and p equals 0, where I just have a CFT of a free compact scalar. And this is just a statement that if I have a holomorphic current, I can multiply any holomorphic function and it remains holomorphic, or an anti-holomorphic version of that statement. And the commutators of this of two of such holomorphic charges essentially yield a central term, which if I mode expand in Fourier coefficients, if you want, it gives rise to a Kac-Moody algebra, the U1 level K Kac-Moody algebra. In higher dimensions, these commutators are again spectrum generating, and they define for me an infinite dimensional current algebra, which I will use to pin down my spectrum. And to do so, I need to massage these things into a mode algebra. I need to expand in modes. And doing so, I get a very simple thing. I get just a bunch of decoupled oscillators where the energy is just the square root of the eigenvalue of the Laplacian on this manifold that I'm quantizing my theory on. So previously, sigma was a submanifold where the charges were defined, but since it's a codimension one submanifold, I can use it as a Cauchy slice. I forgot to say that I'm always in Euclidean signature. That's not, there's no time, that's just temperature. And I should not forget that I have zero modes, which obviously I will not see in the algebra. But they're very important because essentially they are given by the original higher form charges that I had before. And these are labeled by two vectors of integers. And b, p plus 1 and b, d minus p minus 1 here are the Betti numbers of the Cauchy slice. So I'm in a topologically non-trivial Cauchy slice, so I have various cycles of various dimensions, and the zero modes are labeled by those things. Essentially, the fluxes. The Hamiltonian is again very simple. It's just this bunch of harmonic oscillators, decoupled oscillators, and the zero modes. So I can solve it for free. I know how to solve the harmonic oscillator, so I know how to solve generalized Maxwell theory in topology. Essentially, the representation theory of this algebra is given by a bunch of primary states, so states of fixed fluxes that are annihilated by all the lowering operators, then have this energy, delta Rs, which are just R squared plus S squared, essentially. Where here, sorry, I forgot to mention before that this K, which was the level of the Kac-Moody algebra, in this case is related to the gauge coupling of my theory. As, say, for example, in 2D, also, for those of you that know, it was related to the radius of the compact scalar. And the descendants are just for free, essentially. I just act with creation operators. And I raise the energy by En. And since they commute on different levels, I can just act individually. And the generic state is just this. A product of creation operators acting on the primary states that have this energy additive. Very good. And as a non-trivial check, that what I did is first of all correct, and secondly not necessarily super trivial, is I can compute the characters of this algebra. So I have this Kac-Moody algebra. I can assign a character of this algebra, essentially the trace of Q is some formal parameter for now, to the Hamiltonian over these Verma modules that are defined over each primary state. Yes. And then I can resum all of these to get an extended character. And what I get out is, first of all, something that agrees with this purple thing here, which I've computed through a path integral of this on this manifold. And secondly, something that's very reminiscent of two-dimensional CFTs. It's just a Siegel-like theta function. It's just sum over Q to the deltas over an eta squared, similar to the Dedekind eta function, but here it depends on the spectrum of the Laplacian instead of just n. Very good. So now I can put this thing to use and derive some results about CFTs and about gapped systems afterwards. So let me begin with a claim. Any unitary CFT in 2p plus 2 dimensions, so this claim is by Diego Hoffman and Nabil Iqbal, any unitary CFT in D equals 2p plus 2 that has a p-form U1 symmetry has a realization in terms of free p-forms. And the sketch of the proof of that is a very elegant proof, so I'm going to show a sketch of it, is that if I consider the correlator of two currents, it takes a very particular form, such that if I act with the exterior derivative on that, I get 0. I get the DJ correlator is 0. But this is a unitary CFT, and this is the norm of a state generated by the operator DJ in this unitary CFT. So its norm is 0, so the state must be 0 itself. I guess for D equals 2. For energy? Oh, thank you. I'll update the references then. Thanks. Very good. So in D equals 2, it's a standard result that, is it also for generic P?
It's for all fields, yes.
Oh, very good.
Things that saturate the
Right. It's a different argument, is it? It's not that exact argument.
It is exactly that argument.
Okay, very good, thanks.
Slightly more abstractly, because he's not using, actually, there's also unpublished work by Witt that is exactly that argument.
I see.
But Weidberg generalizes this just looking at this.
Perfect, thank you very much. I'll ask you the exact reference afterwards. All right. So in D equals 2, it's a very standard result that we use very often in CFT, that every CFT with a U1 symmetry lies somewhere on the circle branch of the compact scalar, or on the circle branch of the compact scalar, just that. In D equals 4 is a similar result that tells you that there are just photons if I have a U1 one-form symmetry. And it's this setup that I'll be in for the next few slides. And it gives a precise state operator map for non-local. So what I'll get from here is a precise state operator map for non-local operators. And why is that important is that it sets the stage for understanding higher dimensional CFTs on compact manifolds better than we did before, a la Moore-Segal axioms and so on. Sorry, Moore-Seiberg axioms and so on. Very good. This is due to symmetry, essentially, because such a correspondence is not possible for generic CFTs, as these people inform us. So very good, I'll stick with D equals 4, meaning P equals 1, and I'll quantize my theory in a specific manifold, which I'll take to be S2 cross S1. Why? Because it's easy, because I can have a unique holonomy and a unique flux there. And what I'll do is I'll recover the spectrum of states, all the states that I described for you before, by doing a path integral on a manifold that bounds this surface. So I'll take 3 ball times an S1, and I'll insert line operators on the S1 at the center of the ball. And that will give me all the states. But now, this may seem at first trivial, but there is a surprise that if I don't insert anything, I don't get the vacuum, in contrast to two-dimensional CFTs and just the state operator map for local operators. But why is that? Because I don't have a Weyl transformation mapping me to the plane, essentially, or to the Lorentzian cylinder R cross sigma here. And therefore, radial evolution on this ball mixes the ladder operators. So instead of satisfying that this state that the vacuum, the identity operator creates, is annihilated by these guys. It's annihilated by a linear combination of creation and annihilation operators. So there's a Bogoliubov transformation happening. But we know how to deal with these things. There's just a squeezing transformation that we need to do. So it prepares for me a squeezed vacuum rather than a regular one. So this is something that the squeezing transformation has a lot of photons in there, because it has these modes A, N, and A dagger N that are made out of modes of the current, so modes of the photon. So essentially, the vacuum is prepared by inserting photons of all frequencies smeared around this S1, which is consistent with the work of Belan, de Boer, and Kruithof. So the rest, once this is understood, is more or less straightforward and is what you'd expect. The primary states are given by Wilson and 't Hooft lines, so these lines that I talked about before, but just adding them now, e to the I, well, I have them there. E to the I integral of A and e to the I integral of the magnetic guy, dressed with this squeezing transformation to undo the radial evolution. And then the descendants come for free because it's just representation theory, and I've done that previously. So I can just act with, well, the dagger of what killed those guys, and then unsqueeze them. So very good, that's it. And that's the generic state. So the generic state is a bunch of Wilson and 't Hooft lines, a bunch of photons afterwards, and unsqueeze. So that's the entire spectrum. And now I'll switch gears. Right, sorry, yes. They're the fluxes. They're integers, the electric and magnetic flux. Any other questions before I shift gears? Very good. So I'll shift gears. And I'll put on a condensed matter person hat. So now I'll be interested in topological order. And what is that? In one of its kind of more layman definitions, this is patterns of long-range entanglement. So if I get a quantum many-body system, and I quantize it on some Cauchy slice, that I'm not interested in the whole Cauchy slice, I'm just interested in the sub-region here, R, which has a boundary. Then Kitaev and Preskill and Levin-Wen in 2006 tell us that if I calculate the entanglement entropy of that, associated with the sub-region R, on some, say, some state, some global state, this gives me a term that is proportional to the length of the boundary of this entangling surface, partial R, over some UV cutoff that I needed to introduce to regulate the interactions of things inside R and things outside R. Okay, that's usual, but I get a constant negative correction that does not scale with the system size at all, and is given by the logarithm of what's known as a total quantum dimension, so the total number of anyons weighted by their dimensions, in some sense. So for me, the use of that is that its infrared description is in terms of three-dimensional TQFTs. And it lends itself to a sort of bulk edge correspondence by means of anomaly inflow, or more recently symmetry inflow, in terms of this sort of symmetry TFTs, if you know. And a very interesting equality that the entanglement spectrum of this theory, so the spectrum of the modular Hamiltonian, essentially, if you want, is the same as the spectrum of edge modes of this theory, in some precise sense, made precise by these people there. And more than that, and importantly for this talk, its edge spectrum is organized by a Kac-Moody algebra. So what I'm going to do in the next few slides is I'm going to consider higher dimensional versions of that and study the entanglement. And remember this formula, there's going to be a very similar one. All right, so the theory that I'll be considering is the low-dimensional, the infrared description of a theory of surface net condensates. So in 2+1D, in 3D, many topological orders, sometimes it's claimed that all of them, are described by string net condensations. So here I'm going to be considering surface net condensations. And the infrared description of that is what's known as a BF theory. There's a D minus P minus 1 form, B field, and a P form field, A, and they're coupled by this action. And here K is an integer, is a level. What's important here is that this is a gauge theory description of the theory. So there's gauge invariance that I can shift A by any closed thing, and it should describe the same physics, and similarly for B. However, if I put my theory on a manifold with a boundary, the gauge transformations that survive all the way to the boundary give rise to global charges. And here, the sigma will be the Cauchy slice that I'll be interested in. And if this has a boundary, which means like think before as R will have a boundary here. This defines for me conserved charges. And if I get these charges and compute commutators, I get something that has to look familiar based on the previous slides. It's basically these Kac-Moody algebras that I've been advocating for the past 20 minutes. And indeed, if you calculate the edge mode theory that's compatible with this, it's just three p-forms linked together by a chirality condition. It's basically a higher dimensional analog of two copies of the chiral boson, essentially. Since in 3D, BF is two copies of Chern-Simons, if you want. This is two copies of the chiral boson, but with different form degrees. And indeed, its edge spectrum is controlled by these infinite dimensional current algebras that I introduced. So I can put this to work and calculate entanglement entropy, which is formally given by this expression that I take a pure state or any state I want, I reduce it on this subregion. There are subtleties associated with that. Since I have a gauge theoretic description, the Hilbert space does not factorize, so I need to take care of to do so. Fortunately, there is a solution, actually multiple, and not all of them agree with each other, but yes. And there are also UV issues by the introduction of the boundary. It's similar to what gave rise to this L over epsilon term that I had before in 3 dimensions, whose solution is to regulate the trace with some edge Hamiltonian, some quadratic Hamiltonian, the most relevant Hamiltonian I can think of. And doing so, altogether I get, so first of all, I'll be using this replica trick to get this formula. This is an exact equation, formally. So I'll be interested in the trace of rho reduced to the n. Altogether then, this trace takes the form of this extended character that I had before. So this theta over eta, and now we're exactly in business, because we can extract the entanglement by essentially the modular properties of this theta function, this theta thing, and some hard work for eta because it's not as nice as the two-dimensional version of it. But nonetheless, I get a precise result. I get an entanglement entropy that comes in falling powers of L over epsilon. Here, L is the characteristic length of the boundary. That go like d minus, that fall by powers of 2. The first one is d minus 2. The second one is d minus 4, and so on and so forth, whose coefficients are proportional to the heat kernel coefficients of the Laplacian on the manifold that I'm interested in. In even dimensions, L to the 0 is of course a logarithm, so I get something else again here. And then I get a constant thing. Of course, as was mentioned in previous talks, in even dimensions I can fully absorb this thing inside the logarithm, but in odd dimensions I get something that is a universal subleading piece that is the exact higher dimensional analog of topological order. And moreover, I also get this bulk edge correspondence that I had before, since I have, well, I didn't mention all of this, but I could compute it directly either in the extended Hilbert space perspective or via an edge mode path integral. So yeah, this is a higher dimensional version of the topological entanglement entropy. And this brings me to the gift ideas with some time to spare, which means I was a bit fast. Yes, I'll take less than that. And the gift ideas, the gift ideas are as follows. First of all, there's a further generalization of the notion of symmetries. Since I have some time, I can dwell on it a bit. Where the relevant symmetries for me are that I can, if I have, say, stick to the case p equals 0, where I have a compact scalar. The compact scalar has a charge conjugation symmetry, where j goes to minus j, or phi goes to minus phi, if you want. I can gauge that symmetry, and the U1 symmetry that I had before on the compact scalar is broken. but it can be restored as a non-invertible version of it. So non-invertible symmetries are things that are symmetries that have topological operators but do not fuse to a group law. Any case, it is restored, and so is the current algebra. So I have formulas like this, which are the non-invertible versions of the current algebra, that should, in principle, fix the spectrum exactly. And this is some thoughts in progress with Jeremias Aguilera Damia, Ricardo Argurio, and Smedip Chaduri in Brussels. Now, another approach one could have is about linearized gravity. So there's a sense in which if I take gravity in 4 dimensions and linearize the graviton, this theory enjoys what's known as biform symmetry. So you can view the conserved current is R, essentially the Riemann tensor minus some traces. And you can view it as a biform symmetry in the sense that the symmetries of the Riemann tensor are antisymmetric in the first two, antisymmetric in the second two indices, symmetric in the exchange of the two. So this is like two forms with some random stuff between them. In any case, it has this, and it has the Hodge dual version of that as conserved currents. So it has to lead to a sort of current algebra again, where in this case it should depend on more parameters, so things are a bit more murky. It should depend on 2 Killing-Yano tensors and 2 one-forms. Nonetheless, one can perhaps use it to derive some implications of that regarding the linearized spectrum or the asymptotic symmetry and so on. There are some, again, thoughts in progress. And perhaps to get away from the free regime, one could think about non-linear versions of what I said, say Born-Infield type actions instead of just the regular action, the regular Maxwell action, where the current algebra is still there, but the interpretation is a bit more subtle, so I don't know what to do with that, but it's something that I should do at some point. And with that, thank you. Yes.
So everything seems to begin from the very beginning in the equations of motion.
Yes,
So
yes.
how does this hit you?
Very good. So this will hit me in the, maybe I should go back to the equations. Oh. Too many equations there. So here, instead of having these simple twisted self-duality conditions, one of these two terms will be multiplied by a function of the fields. So now instead of imposing this equation globally, since these are just functions, external functions that you give me and I put there, I should impose that as a word identity. So as an operator equation. And from this, things should follow, but it's unclear how precise. It should organize exactly the spectrum again, but it needs some clever tricks to work, and I don't know what the clever tricks are. Yes, yes.
I think Euler, Heisenberg left first term.
Yes.
The theories, they should come with a unique at all.
Exactly, yeah.
And how will this talk be executed with?
Very good, very good.
Maybe you can follow the
Probably you can derive a sort of derivative expansion from that if you want. It should organize it like that. I'm not entirely sure how this will work in practice. Yeah.
Your second part about the diagram and entropy, can you go
Yes,
to the slide?
of course.
As you said, the number of substances.
Which slide do you want? This one, I guess. Yes.
Yeah, yeah. So as you said, the sum is the fact that the space has a factorized
Yes.
UV issues, and as you said,
Mm-hmm.
people have found some ways around it.
Yeah.
How much do the results differ?
Very good.
Are they robust or are they?
So for the second part is slightly easier in the sense that this is just the most relevant term you can write. It should not depend so much, and it ties with Carlos's question that the rest would come with a UV cutoff and so on. And I guess the relevant part of your question is the first, right?
On your slide with formulas now, where you had to the result as well.
There.
If I reparameterize epsilon, I can still change the finite part.
In even dimensions, yes.
Not just in all dimensions.
What? Sorry?
Change epsilon by.
No. In odd dimension, this thing vanishes.
Yeah, I know. So I'm just going to use the power law. Change epsilon to epsilon
absorbs things. Okay. But how is that affected in 2+1D? Because in 2+1 is very robust. So there's no topological order?
That is the same. I think the words people are using is in scale, and if you only want to focus only on
Yeah.
scale, it's the IR scale.
Well,
Why
yes.
you
Yes.
aren't allowed to do this.
Well, essentially, the point is that this is a topological theory, so it should really, it's entanglement entropy should not know so much about the UV. It's just these fake things that we've introduced, these edge modes, no?
Yeah, I mean, that is the shoot and also what the formulas tell you.
Yes.
So in a
Yeah.
sense, you chose some regulator.
Yes.
And
Well, the regulator is the standard one, right? It's just the quadratic Hamiltonian. Well, first of all, okay, let me rephrase. The regulator is chosen such that the two methods that I have to compute the entanglement entropy agree, and that's a unique, essentially one. The first issue actually depends a lot on what you try to use to resolve that. Well, there's one standard way to resolve it in terms of the edge modes. This extended Hilbert space is more or less the standard way. One other thing you can try to do is an algebraic point of view. And actually, we've done that with Jackson Fliss in a different paper, and the entropy is different, so it's counting something else.
I see. So it really depends very strongly
Yes.
with
Yes.
So, is there some concrete like kind of consequence for like with these statistical algebras? Like for example, in the Owen vector model, like,
Mhm.
does it tell you something new?
Does it I don't know really. I haven't thought about the Owen vector model and how much it constrains it. Well, said differently. Okay, maybe one connection I can try to extrapolate towards is sort of it. There are a lot of ifs there. Having these Kac-Moody algebras could, or a lot of could result in a higher dimensional version of a Kosterlitz-Thouless point in the moduli space of theories, which you can use to start a dimensional expansion, sort of d plus epsilon expansion of the theories, in the hopes to land on a vector model, but as a UV model here. So maybe this is one use they could have. Not very concrete, but it's one idea that came to mind.
Can I also ask something? You have all these modular functions. Is there a
Yes.
notion of modular invariance that we can define?
That's a very good question. Not a very clear one, except for if I have two circles, I should be able to exchange them. But I don't know of a clear like modular group that should be. And I don't think people know in general.
Thank you. Okay, we arrived at the last talk of today from Riggers AI on exceptional cluster algebra for Higgs plus jet production.
Hi everybody. First of all, thanks for staying here until so late. And thanks the organizer for giving me the opportunity to present my work. I have been following this workshop since its first version, and it's the first time that I'm able to speak in this. I will talk about joint work with my supervisor, Georgios Papathanasiou, that is about to appear in the Journal of High Energy Physics. And I hope that by the end of this talk, you will be able to understand the words in the title. Okay, so we're interested in understanding the fundamental constituents of matter and the way they interact together. Central to probing physics at these scales are collider experiments. During such experiments, for example, beams of protons, let's say, are accelerated to very high speeds, and they are put to collide in some certain point in space, producing pictures like this. What we see here is an image I took from CMS-CERN in 2012. This is exactly the year where the Higgs particle was observed. And the green towers, as well as the dotted yellow lines here, resemble structures that are expected from the decay of the Higgs particle into photons. The rest of the picture does not have to do with the Higgs particle, it's just background processes. As theorists, we want to be able to describe such pictures in mathematical frameworks. In the modern era, the way to do so is through quantum field theory. This is the framework which describes the elementary particles and the interactions between them. In particular, we are interested in scattering amplitudes. So pictures like this essentially give the experimentalists the opportunity to calculate probabilities of certain processes to occur. And in the context of quantum field theory, the scattering amplitudes are are probability densities of such processes to happen. We need to have better theories in order to match the experimental results that are coming in the near future. Much more due to the expected high luminosity Large Hadron Collider launch by 2030, which is expected to provide us with experimental data with percentage precision, and this will really test the ability we have to make precise theoretical statements. So let's see how, in the context of quantum field theory, one is able to compute scattering amplitudes from this cartoon. In the left-hand side, you can imagine two particles entering some area and then coming out. The gray blob is essentially representing the scattering process. And in the right-hand side, we have a perturbative expansion in some small constant, which for the purposes of this talk can be thought to be 0.1. And the corresponding terms in these expansions are called Feynman integrals. They are represented by these graphs. Each graph has an analytic expression of an integral. And we define the loop order to be essentially, you can think of it as the number of loops in the graph, but otherwise it's the number of momentum integrals we need to take in the Feynman integrals above. As I said earlier, usually in experiments as such, protons are being collided. The major force by which these interact is the strong force, and in the context of quantum field theory, this is described by quantum chromodynamics. Us wanting to be able to describe, to have theoretical predictions with higher accuracy means computing more and more of these terms, which becomes hard. Okay? Increasing the number of particles and the loop order leads to complicated multiple momentum integrals of the internal momenta, which are generally too hard to compute. Up to date, the current machinery allows people to produce results almost for all processes of one loop. There are results for two loop, and this is actually the current efforts. There are also three loop results, but to a lesser extent. Okay, so one way of proceeding in order to also match. Yes. Yes, of course. Yeah, so as I was saying, in order to match the upcoming more precise experimental data that are expected from 2030, we need to be able to resolve all the two-loop calculations of the scattering amplitudes. One way of proceeding is to really try harder to compute these integrals, but we propose an alternative way. We shift to a different theory, in particular n equals 4 Soup and Yang-Mills. This is a theory which possesses symmetries that we know are not physical. For example, they are supersymmetric, conformal, dual conformal, in some sense integrable. We can look at this theory for ideas. It can work as an idea theoretical lab for us to understand better the structure of quantum field theories and maybe draw ideas for common use in QCD amplitudes, let's say. Okay, let's delve into these kind of ideas. First of all, we will speak a bit about canonical differential equations. These were initially developed by Hen in 2013 in the context of n equals 4 Chopin-Yang-Mills for some dual conformal invariant integrals, and today are common practice in the community of Feynman integration. The idea is that, as commonly known, integrating is much harder than differentiating, and therefore let's try to swap the integration by deriving a differential equation for these Feynman integrals and solve this instead. These differential equations take this form, and let's delve a little bit into their structure. In the left-hand side, we have a derivative on f. F represents the Feynman integrals. These depend on z and epsilon. The integrals, apart from being very hard to compute, are also very often divergent in the context of quantum field theory when we evaluate them at 4 dimensions. To have a better analytical control over their mathematical expressions, we shift from d equals 4 by a small parameter epsilon, and therefore our integrals depend on this. Then z represents the kinematic data, that is the momenta or the masses of the particles that we want to describe their collisions. And then we move to the right-hand side. There is a proportionality constant epsilon. This represents a matrix. The matrix consists of the logarithms of functions of the kinematics called letters, which are multiplied by constant matrices. And then this whole expression is multiplied again by the integral that we are interested in. The form of this equation allows us to make some observations regarding the analytical structure of the integrals. So first of all, by the very structure of the differential equation, we see that whenever these alphas go to 0 or infinity, the form of the differential equation diverges, since it is the argument of the logarithm, and therefore it is expected that the Feynman integrals develop some branch cuts. Moreover, there is more information to it in the constant matrices AI, which are described by what is called adjacency restrictions, and they take this form. Essentially, what they tell us is that this function that we have that develops some branch cuts on these alpha i's, we can take discontinuities around these branch cuts, and there are certain discontinuities, certain consecutive discontinuities, let's say on alpha I and then on alpha j, which vanish. Therefore, if we take, let's say, the monodromy around them, the result is 0. These two pieces of information will be central in the rest of the talk. Yes? Yes. To derive such equations, canonical differential equations, one needs to use dimensional regularization. To preserve gauge invariance in general, this is the main motivation, but in this particular context, this can only be done in dimensional regularization. The central idea for deriving such equations is to have good analytical control of the integrals, which is easier in this way. Okay, that's it with canonical differential equations. There are many more ideas drawn from n equals 4, such as generalized unitarity or the symbol map. Again, these were initiated in n equals 4 Chopin-Yang-Mills and now are common practice in the field of Feynman integration. But today we are here to speak about cluster algebras. These mathematical structures were first introduced in the context of n equals 4 Chopin-Yang-Mills, and they found to describe the analytic structure of 6 and 7 particle scattering amplitudes. Their existence was somewhat expected from the internal symmetries of this theory, and they were heavily used to fully compute the 6 and 7 particle amplitudes to unprecedented loop orders. In particular, the 6-point amplitude was computed up to 8 loops, and the 7-point particle up to 4 loops. Note that when I say bootstrap, I mean the previous picture of the scattering amplitude being written as an expansion over the coupling constant is not necessary in this case. The full amplitude was computed only based on the analytic structure, which was defined by the cluster algebraic structure. Okay, so it seems like cluster algebras, we have a reason to study them. Let's see what they are. You can think of a cluster algebra of rank D as a certain set of special rational functions with a number of properties. First of all, we have the cluster variables, AI, which generate the cluster algebra. Then these cluster variables are distributed into subsets of cardinality D, which is the same of the rank of the cluster algebra, and these are called clusters. The algebra is generated by starting with some initial cluster and then applying some predefined rules which are attached to the type of the cluster algebra, and these are called mutations. When this iterative procedure of the mutation ends, giving us a finite number of cluster variables, the corresponding cluster algebra is of course called finite. They are fully classified in the literature, and their classification is in one-to-one correspondence with the one of semi-simple algebras. The full list of finite cluster algebras are these here, exactly the same as the semi-simple algebras. The index represents the corresponding rank. Note that these four, mimicking the jargon of semi-simple algebras, are called exceptional. This, of course, will be important later. Okay, this was a general picture. Let's see an example. Let's study the G2 cluster algebra. This is a cluster algebra of rank 2. Therefore, all the clusters have 2 elements. In particular, we can start from an initial cluster with cluster variables A1 and A2. Then apply this mutation rule consecutively and derive the cluster algebra. We get 8 variables, but let's do that step by step because probably it was very quick. We start from A1 and A2 and start applying the mutation rule. Let's say we start the mutation on A1. We get A3, which is this rational function. We move on to mutate on A3 this time. We get A4. And if we keep doing this 7 times, we end up to the same cluster, namely A1, A2. This convinces us that we have to do with a finite cluster algebra. Note that the picture we ended up with, first of all, is an octagon, and second, it conveys all the information of the cluster algebraic structure, that is, both the 8 cluster variables as well as the mutations that gives them as well as the clusters that we obtain through mutation. Such graphs are called exchange graphs, and they will also be important later, so keep this picture in mind. Okay, this is all good. Now we know what cluster algebras are. We said... Sorry, can you repeat?
Why the specific mutation?
I'm hiding a lot of stuff here. In practice, cluster algebras are not really defined the way I define them. There is also some quiver involved, and the arrows of the quiver really define you in a very specific way how the mutation looks like. This is just a simplification. I know that they appear in this context, but when one studies cluster algebras on their own, the quiver really tells you how to mutate on its own. So the information of the cluster algebra is actually coming from the initial cluster as well as a quiver. I hide this information here. There is a there is a matrix involved that is anti-symmetrizable, and it is the same metric, the same Cartan matrix, which appears in the context of semi-simple algebras. That's where it draws the name from. Yes. The Cartan matrix is everything you need for this. Okay, so are these useful in any context? Can we use them for the real world? There are hints that this can indeed be the case. There have been examples where cluster algebras are related to alphabets of Feynman integrals relevant for the real world, from works of Tchicherin and Papathanasiou, as well as He, Yang, and Li. Today we will speak about integrals related to Higgs plus jet protection. One of the processes involved in the heavy top quark limit, one of the processes involved is the following one. The Higgs decays into 3 gluons. The jet essentially represents the fact that gluons cannot be free, therefore they recombine to produce mesons and counts, and these are detected in the detectors of the experiments are as beams with the same transfer momentum. This is roughly what is called a jet. But we are just interested on this part of this amplitude. So for this particular case, it was found that both the one loop and the two loop alphabets are related to cluster algebras, in particular the A2 and the C2 ones. Okay, this is very nice, but a recent computation of the following Feynman integral revealed 2 new letters which fail to be described by the C2 cluster algebra. Let's look at this picture for a second. We have the Higgs particle with some momentum P4, and then the gluons with momentum P1, P2, and P3. The gluons are, of course, massless, and the Higgs is massive. That's why it is in bold. This is a through-loop process, and by using these kinematic variables, Z1 and Z2, it was found that this is the alphabet describing the canonical differential equation for this Feynman integral. Until here, we find the 2 new letters. These are all polynomials. The new letters are second-order polynomials. So is this the end of the story? Is this the end of the relevance of cluster algebras in the real world? Thankfully not. We managed to find the transformation of the kinematic variable Z1 and Z2. We applied this transformation in the form of the canonical differential equation. This gives a new differential equation in variables A1 and A2 with some new sets of letters, and these new sets of letters completely identify with the cluster variables of the G2 cluster algebra, validating the equivalence of these 2 alphabets. So in other words, one can choose to either compute this Feynman integral in the Z1 and Z2 variables, and then they will have the alphabet above, or they can choose to compute it in the A1 and A2 variables, and the alphabet will be given by the G2 cluster algebra. This is fantastic. But is there anything more? So in addition to the alphabet changing, also the constant A matrices that I mentioned before change. They change in a way that they actually produce new adjacency restrictions for the canonical differential equations, and we managed to identify them. These, even if they were initiated by the computation of just one Feynman integral, which remember is just one part of the perturbative expansion of the amplitude, these relations were recently verified for the full, not for the full, but for partial results for the Higgs to 3 gluons amplitude. This is a 3-loop result. It is the C2 cluster algebra at 2 loops. For the amplitude? Yes. Yes, exactly. And thanks for the question, because I remember that I said earlier that the current situation is mostly computing 2-loop results, but 3-loop results are extremely important to match with the upcoming efficiency of the High Luminosity Large Hadron Collider. Sorry? This is one of these cases, exactly. Okay. This is very nice, but thanks. At this point, so far we are agnostic on why these expressions really appear. Why would the A matrices have such relations? In other words, what question do we need to pose to the cluster algebra such that the answer will be these relations? When they first appeared in the context of n equals 4 Supping-Yang-Mills theory, this question was answered by the cluster adjacency principle. This simply states that product of these matrices AI and AJ vanish whenever the corresponding variables A1, AI, and AJ do not appear together in any cluster. We saw previously in the exchange graph that not all variables appeared together, but there were only 2 slots available for each variable in each cluster. Therefore, there are many variables that do not appear together in clusters. This leads to many of these relations. Okay, let's take this principle at face value and apply it for this case. Unfortunately, this principle predicts 40 relations, but the actual amplitude only has 20 of them. What can we do better? What other adjacency principles should we come up with to match with what we get in our example? We tried to look into this a little bit more by the following main idea. What if we could take the G2 cluster algebra and embed it in some bigger cluster algebra? This way, our variables will have more space to appear together in some higher cluster algebra, giving less restrictions. Okay, let's look at the exchange graph of the B3 cluster algebra. Again, as in the G2 example, each vertex here corresponds to a cluster, and its edge corresponds to a mutation between the clusters. This is a question for the audience, whether you can identify a G2 cluster algebra here that is being said an octagon. We are just looking for an octagon. As we said earlier, the octagon completely identifies the characteristics of the cluster algebra. Okay, I know it's very late, so I will just say it. It lies on the intersection between these planes, between this plane and the B3 exchange graph. If you connect these points, you can convince yourself that there is an octagon there. Okay, let's see. Do you get anything better this way? Indeed, as expected, since the cluster variables have more space to be together in some, if not G2 cluster, they can be together in some B3 cluster, therefore giving less adjacency restrictions. So from 40 that were predicted before, now we get 28. On top of that, the 21 that we observed are a subset of this 28. It seems like the amplitude itself knows about the cluster